Hey guys, you can call me Cherry Odier here, and I am a student from the Liverpool University, and I am majoring in applied mathematics. And today I will introduce one subject of my school, population dynamics and microeconomics. And today the topic I choose is the interacting species from the population dynamics. Okay, first let's take a look at the types of interaction. Competition, predator and prey, host, parasite, and cooperation. And in order to simplify our analysis, we only consider two species in our interaction. Okay, now let's construct differential equations for xt and yt as follows. dx dt equals to basic model for x species as if it were alone plus interaction term, and the form of dy dt is the same as dx dt above. Okay, now let's separate dx dt into two parts. The first part, the basic model for x could be a linear model Rx with constant growth rate R, or if we want to have a model that is more close to the reality, we could use Rx 1 minus x if we want to account for limitations on resources. Okay, and the next, second part, interaction term. We can obviously say that the interaction term contains two variables, x and y, because the existence of the both species will influence each other, and mathematically, in this term, it will contain both x and y. Ultimately, we want to know how solutions xt and yt each vary with time, so that we can predict the future sizes of the two populations. So how to deal with the differential equations? Okay, and the approach is given as below. We will get certain hints about their behavior by looking at the stability properties of their equilibrium points. Okay, this concept is very important to us. Equilibrium points. Okay, now let's look at the definition. Definition, equilibrium point. Okay, this sentence is chosen from our lecture notes, and I will explain it in a very simple way. dx dt equals to 0 and dy dt equals to 0. This means that at the equilibrium point, the change rate of xt and yt is equal to 0. That explains the word equilibrium. Okay, so as we can see, we need to look at the stability properties of their equilibrium points, and here is our question. How can we examine the stability? Okay, consider a system of ODE, dx dt equals to f1 and dy dt equals to f2. Here, f1 and f2 are functions with two variables, x and y. Okay, now suppose we have already know the equilibrium point, xeq and yeq. And here, we want to examine the points around xeq and yeq, and we will introduce a concept from the mathematical analysis, the neighborhood. And in the analysis, we call the neighborhood x plus epsilon and y plus epsilon, and here we introduce the concept. Here, x and y represent some point displayed slightly from xeq and yeq, and we will use the new variable epsilon1 and epsilon2 here, and x equals to xeq plus epsilon1 and y equals to yeq plus epsilon2. Okay, since we have already changed the variables, and the variables in our ODE should be also changed. Here we have dx dt equals to dy dt and equals to f1, like this. And dy dt is like this. Okay, so looking at the functions given, we can know and we can imagine that the function f1 is very complex, since first we have two variables, and second, it is not linearized. We can imagine that we have the terms like x, xy, right? So using the normal solution approaches to deal with these functions is very difficult, and we need to again introduce a new concept from analysis, and also our weapon to deal with such kind of situation. Yeah, the Taylor's theorem. Taylor's theorem is a strong weapon to deal with a situation like this. And let's recall this concept again. Fx equals to fa plus the first order derivative of a of fx at the point a, and x minus a plus the term at here, right? And Taylor's theorem can help us to approximate the differential equations above into a linearized functions. So how should we deal with this? We also have problems here. The first one, yeah. In this functions, we only have one variables. However, in the differential equations above, we have two variables, epsilon1, epsilon2, x and y. And second is what? let me take a second to think about. Yeah, so the main problem is we have more variables, and this one has only one variable. So we can but this problem is not so hard to deal with, because we can make a comparison between these two questions. Yeah. First here, the derivative in the multivariable functions, we can use the partial derivatives to deal with it. And let's make a comparison between it. And fx, here it is fx. And fx in our differential equations is here, f1. Here we will take f1 as an example, and f2 will be the same approach as f1. Okay, here, fa, and in our ODE, fa will be the value of f at the equilibrium point. And here, the first order derivative of f, and here, we need to introduce the concept of partial derivatives. Yeah, a partial derivative of what? In the example here, it is the derivative of fa. In our ODE, it is the derivative of fx at the equilibrium point. And second, the partial derivative of y at the equilibrium point. Yes. That's the comparison. That's the similarity between these two functions. And here, this is the second order of the infinity small. And here I will give the approximation equations below. Yeah, see, f1 equals to this function, and f2 equals to this function. In this such kind of form is very helpful for us to examine the properties of the function. And here we will ignore the small terms. We can treat it as 0. And again, the value of f1 and f2 at the equilibrium point is 0. So the final function will be simplified as follows, and we will use the matrix form and vector form to express it. We will finally get this one. So let us focus on this matrix. This matrix is just the coefficient of epsilon1 and epsilon2, right? And here we will introduce a new concept. We can get community matrix from the equation above. And also it has a name called Jacobian matrix. Okay. Observing the given equations, we can probably guess that the properties of this matrix, or properties, eigenvalues and eigenvectors, are very, very important to the properties of stability of an equilibrium point. And let's look at this form of functions again. It is perfectly in the form of du dt equals to au. And let's recall again the concept in the differential equations. Differential equations x and exponential at. When we get the ODE systems in such kind of form, we can immediately get its general solution. The general solutions are epsilon t equals to blah blah blah. And here, lambda 1 and lambda 2 represents the eigenvalues of this matrix, and EB1, EB2 here represents the corresponding vector. And in the next video, I will introduce to you about how different eigenvalues will influence the stability properties. Okay, thank you very much.